Welcome back to the deep dive. You've handed us a stack of sources centered around a truly seminal paper, one that fundamentally changed how we build systems that learn to interpret complex, variable data like images.
Ah,
We're diving deep into gradient-based learning applied to document recognition, published back in 1998 by Yann LeCun, Léon Bottou, Yoshua Bengio, and Patrick Haffner. I mean, names that are absolute pillars in the world of machine learning today.
yeah, this paper is it's much more than just a historical curiosity. It really presented a powerful vision for tackling these real-world challenges, problems involving complex data and sequences of processing steps.
Right.
Think about the problem they were facing. Document recognition. It's not just spotting a perfect letter A.
No.
It's dealing with messy handwritten digits that vary wildly, characters that are touching or overlapping, and needing to string them together into meaningful sequences, like reading an amount on a check.
And the traditional way of solving this was kind of like building a Rube Goldberg machine, wasn't it? You'd have all these separate components, one piece to find the text, another to try and chop it into individual characters,
Sure.
another to recognize each character, and maybe something else to check if the sequence even made sense linguistically.
Precisely. And each of those components would be optimized totally in isolation.
Yeah.
You train your character recognizer on perfect, clean examples, right?
Right, completely separate.
But in a real document, the piece that cuts the image into characters, the segmenter, well, it might make mistakes. Maybe it cuts a character in half or lumps two together.
Uh-huh.
And those errors just cascade down the line.
Hmm.
The individually trained recognizer, which never saw those messy cases during its own training, just gets completely confused.
Plus, fine-tuning how those hand-designed, separately optimized pieces interacted. Trying to figure out how to weigh the segmenter's confidence against the recognizer's score. I mean, that sounds like an absolute nightmare of trial and error.
Oh, it was incredibly brittle and time-consuming. The core insight of this paper, the really big idea, is using gradient-based learning as a unifying principle, not just for training a single model, but for training an entire complex system end-to-end.
Okay.
Minimize one overall performance measure,
Yeah.
like the final error rate on the complete document, and just let the gradients figure out how to adjust every single parameter in the whole pipeline.
Okay, let's unpack this then. So, our mission here is to go beyond just summarizing the paper. We really want to understand how they made this end-to-end training possible for such complex systems.
Mm.
We'll need to dig into the key technical heroes. Convolutional neural networks, or CNNs,
Yep.
which were crucial for handling the images themselves, and then graph transformer networks, GTNs, which kind of provided the framework to represent and process the flow of ambiguous information through the system.
Exactly. We'll explore the fundamental ideas of gradient-based learning that underpin everything. Then we'll dive into the specific architecture of CNNs and, the famous Linnet 5 example that really showed their power for image recognition.
Okay.
And then we'll explore how GTNs allowed them to represent complex state information as graphs and train these systems globally. Finally, we'll look at how this whole framework was applied to solve real tough problems like reading checks and online handwriting. We want to extract those moments that make you think, that's how they did it.
Perfect. Let's jump into the deep end. All right, so at the heart of any system that learns from data is this fundamental setup, right? You show the machine examples and it adjusts itself to get closer to the right answer. The paper frames this pretty elegantly.
Yeah, they start with the basic notion of a learning machine is essentially just a function. You give it an input pattern, let's an image of a digit,
Right.
and it has a set of adjustable internal knobs, its parameters. Based on the input and the current setting of these knobs, it produces an output, maybe a score for each possible digit class, like
Yeah.
0 through 9.
And the learning part comes from figuring out how to turn those knobs correctly.
Precisely. You have a desired output for that input, the correct digit label. You measure the difference between what the machine outputs and what you wanted to output. This difference is quantified by a loss function.
Okay.
The loss function basically tells you how wrong the machine's current settings are for that specific example. And the ultimate goal of learning is to find the setting of the parameters that minimizes the average loss across a whole collection of training examples you provide.
But as you mentioned in the intro, minimizing the error just on the training data isn't the whole story, is it?
Now, it's a crucial distinction. The real test is how well the machine performs on new, unseen data, its ability to generalize.
Right. You want it to work in the real world.
Exactly, not just memorize the training set. Now, while theoretical work, and they mentioned some papers, suggest that more training data helps close the gap between training error and test error, The design of the system itself and how you train it are absolutely critical for good generalization.
And this is where the power of gradient-based learning comes in for actually minimizing that loss function. How does that process work under the hood?
Well, if you have a loss function that changes smoothly as you tweak the parameters, and that's important, the smoothness gradient-based learning gives you a systematic way to find the minimum. Instead of randomly fumbling with the knobs or, trying every
And
combination.
that would take forever.
Right. You use the concept of the gradient. The gradient is essentially a vector, and it points in the direction of the steepest increase in the loss function with respect to the parameters.
Okay, so it tells you which way is uphill.
Exactly.
Okay.
So if you want to make the loss smaller, you just go the other way, downhill. You move in the direction opposite to the gradient. This is the core idea of gradient descent. You start with some initial parameter settings, calculate the gradient of the loss function, and then you adjust the parameters by taking a small step in the negative gradient direction.
Okay.
You just repeat this process iteratively, and the parameters should move towards a minimum of the loss function. The size of that step, that's determined by the learning rate, which is a really crucial hyperparameter you have to tune.
Calculating the gradient over a huge training set for every single parameter adjustment sounds computationally massive, though, like really slow.
It absolutely can be. And that's why a crucial practical technique, one they used heavily, is the stochastic gradient algorithm, or SGD.
Stochastic, meaning random.
Sort of. Instead of calculating the gradient using all the training examples before making one single update that's called batch gradient descent, you calculate the gradient using just one example, maybe a small batch of examples, and you update the parameters immediately.
Ah, okay. So you're making updates much, much more frequently, but each update is based on kind of a noisy estimate of the true direction.
That's exactly right. The parameters jiggle around a bit more, you could say. But on large data sets, especially those with a lot of redundancy, like think about thousands of images of different handwritten A's, they all share many features.
Sure.
Processing individual examples for small batches gives you way more updates for the same amount of computation. You're constantly getting fresh information from the data and nudging the parameters. And this leads to much faster overall convergence compared to waiting to process the entire data set for just one single update.
It's almost like learning in real time from one example at a time rather than, say, reviewing the entire textbook before trying a single practice problem.
That's a great analogy.
Mm-hmm.
And they also point out something interesting. This stochastic nature, this inherent noise in the updates, can actually be beneficial for generalization.
How so?
Well, it sort of prevents the parameters from getting stuck in very sharp, narrow minima in the loss function landscape.
Mm.
It tends to push the parameters towards broader, flatter minima.
Okay.
And those broader minima often correspond to solutions that are more robust and generalize better to unseen data. They actually observed this effect in their experiments, like with Linnet 5. Even with a relatively large learning rate that caused some oscillation in the training error, they didn't necessarily see the typical signs of overtraining where the test error starts to climb back up.
Huh. That's a fascinating side effect, that the noise actually helps you find a better solution in the long run. And the mechanism that lets you actually compute these gradients efficiently in these complex multi-layered systems,
Right.
that's backpropagation, right?
Famous backpropagation algorithm. Yeah. While the core mathematical idea, the chain rule, existed earlier in other fields like control theory, its application to training multi-layered neural networks was a massive breakthrough.
So what's the fundamental idea?
The fundamental idea is to efficiently calculate how much each individual parameter in the network contributed to the final error. You do this by starting at the output layer, where you know the error directly, and propagating that error signal, or more accurately, the gradient of the loss with respect to the outputs backward through the network, layer by layer.
Using the chain rule from calculus.
Exactly. Use the chain rule to figure out the gradient for the layer before the output, then the layer before that, and so on, all the way back to the input layer and the parameters connecting to it.
So it calculates the gradient for the final output layer first, then uses that to figure out the gradient for the layer before it, and so on, all the way back.
Precisely. It gives you the gradient of the overall loss function with respect to every single adjustable parameter in the network, no matter how deep it is. This makes gradient descent, or especially stochastic gradient descent, computationally feasible even for networks with, potentially millions of parameters spread across many layers. Without backpropagation, training such deep networks would be practically impossible. It's really the engine that powers modern deep learning.
Okay, so the foundation is this gradient-based learning, fueled by efficient backpropagation, and often using stochastic updates for speed and maybe even better generalization. Now, let's apply this to the specific problem of image recognition. The paper highlights convolutional neural networks, CNNs, as the solution specifically designed for visual data.
Right. CNNs were a critical innovation for getting computers to effectively see patterns in images.
Yeah.
Before CNNs really became widespread, people often relied on manually designing feature extractors.
Right, like coding up edge detectors or corner detectors.
Exactly. Pieces of code that look for specific things like edges or corners, and then you'd feed these extracted features into a standard trainable classifier.
Which sounds like putting a lot of the burden on human ingenuity rather than letting the machine learn everything it needs.
It was. And just feeding raw pixel data directly into a standard, fully connected neural network where every neuron connects to every neuron in the next layer, well, that wasn't very effective for images. And there are a few key reasons why.
Okay, what were the main problems?
First, images are high dimensional. Even a relatively small image, say 32 by 32 pixels like in LeNet 5, has over 1,000 pixels. A fully connected network connecting every input pixel to every unit in the first hidden layer results in an explosion of parameters, millions maybe.
Wow.
This requires huge amounts of data to train properly and is incredibly computationally expensive, both for training and memory.
And images have structure, too. Pixels aren't just a random list of numbers.
Precisely. That's the second problem. Fully connected nets don't naturally handle the fact that patterns in images can appear anywhere. Locality matters. If you train a fully connected network to recognize, say, a feature like an eye in the top left corner of an image, and then the eye appears slightly shifted to the right in a new image, the network likely won't recognize it unless you specifically showed it that exact shifted version during training. It lacks built-in invariance to things like translation or small distortions.
So you'd need tons of data showing the same feature everywhere.
You'd need massive amounts of training data showing features at every possible location and orientation, which is hugely inefficient. The network would end up learning redundant detectors for the same feature at different places. And it also ignores the input topology, the fact that neighboring pixels are related.
So how do CNNs solve these fundamental problems?
They do it with three key architectural ideas. And these ideas were actually inspired, in part, by Hubel and Weisel's work on how biological visual systems seem to function.
Okay, what's the first one?
The first is local receptive fields. Instead of every unit in a layer being connected to every unit in the previous layer, each unit is only connected to a small localized patch of the previous layer.
Like having lots of little windows scanning across the input image.
Exactly like that. Each unit in this layer learns to detect a specific, simple local feature, maybe an edge, a corner, a specific texture, but only within its little window, its receptive field.
Okay, so lots of tiny detectors for simple things in specific spots. What's next?
The second key idea is shared weights. This is the really crucial convolutional part. All the units that are organized into a specific feature map share the exact same set of weights and the same bias.
A feature map.
Yeah, think of a feature map as a 2D grid of units, all looking for the same pattern. Because they share weights, they're all detecting the same local feature, but they're doing it at different locations across the input because their local receptive fields cover different patches of the previous layer.
Ah, okay. So if a detector for, say, a vertical edge is useful in one part of the image, it's probably useful everywhere else too. You don't need to learn a brand new detector for every possible location.
That's the core efficiency gain. By sharing weights, the network automatically gets a form of built-in shift invariance. If that vertical edge appears somewhere else in the image, a different unit in the same feature map will activate, indicating that the feature was found just in a different location.
And that must dramatically reduce the number of parameters the network needs to learn, right?
Hugely. Compared to a fully connected network, they mentioned LeNet 5 had something like 345,000 connections, but only about 60,000 trainable parameters because of weight sharing. This reduction in parameters is great for generalization. It reduces the network's capacity to just memorize the training data and requires less data to train effectively. And the operation of scanning this shared weight filter across the input is mathematically equivalent to a convolution, hence the name convolutional network.
Okay, local fields, shared weights. What's the third idea?
The third is spatial or temporal subsampling, often called pooling. After detecting features and creating these feature maps, you often reduce their spatial resolution.
How does that work?
It's usually done by layers, where each unit computes something simple, like the average or maybe the maximum value, over a small neighborhood in the previous layer's feature map. Then it might apply a learn-to-weight and bias and pass it through an activation function.
Why shrink the feature maps down? What's the benefit?
Well, once you've detected that a certain feature is present, say, that vertical edge, its exact pixel location, becomes a bit less important than its approximate position relative to other features. Subsampling makes the network more robust to small shifts and distortions in the input image.
So it builds in some tolerance for things not lining up perfectly.
Exactly. It helps later layers in the network learn higher-level features that are invariant to minor variations in the positions of the lower-level features they're detecting. It's like abstracting away the very fine-grained details to focus on the bigger picture composed of the detected features.
Okay, so CNNs combine these three things: local feature detectors, shared weights for efficiency and shift invariance, and subsampling for robustness to minor variations.
That's the fundamental architecture, yeah. And Linux 5 is the classic example from this very paper that put these ideas together extremely effectively for handwritten digit recognition.
Let's quickly trace the path of an image through Linux 5, maybe referencing figure 2 from the paper.
Sure. It starts with the input image, a small 32 by 32 grayscale image of a digit. They even normalize the pixel values, which helps learning.
Okay.
The first layer, C1, is convolutional. It has 6 feature maps, each using a 5 by 5 filter, that's the shared weights, that slides over the input. These filters learn to pick up simple features like edges, corners, maybe strokes, in different orientations.
So 6 different basic feature detectors scanning the image.
Right. Then comes layer S2, which is a subsampling layer. It takes each of the 6 feature maps from C1 and reduces their size, typically by averaging 2 by 2 neighborhoods. This shrinks the spatial dimensions and builds in that initial robustness to small shifts.
Okay, convolve then subsample. Does that repeat?
Yes, that pattern often repeats. Layer C3 is another convolutional layer, but it's more complex. It has 16 feature maps, and its 5 by 5 filters look at combinations of features for multiple maps in the S2 layer. So it's learning to combine simpler features into slightly more complex patterns.
Combining edges and corners into maybe arcs or junctions.
Something like that, yeah. Then comes S4, another subsampling layer, reducing the size of those 16 feature maps.
Getting smaller and more abstract.
Exactly. Then there's C5, which is technically convolutional with 120 feature maps and 5 by 5 filters. But because the input maps from S4 are already 5 by 5 at this point, each unit in C5 effectively looks at the entire map from S4. It acts like a fully connected layer here, but they call it convolutional because the principal scales if the input image was larger.
Okay, almost there.
Then F6 is a standard fully connected layer with 84 units taking input from all 120 units in C5. It uses specific sigmoid activation here designed for faster convergence.
And finally, the output.
The output layer has 10 units, one for each digit class, 0, 9. They used a specific type called radial basis function units here, which essentially measured the Euclidean distance between the output of F6 and a learned prototype vector for each class. The closer the F6 output is to a class prototype, the lower the penalty for that class.
So the network outputs 10 penalties, and the lowest penalty corresponds to the predicted digit.
That's the idea.
And training this entire stack, all 7 layers, end-to-end using gradient descent and backpropagation, is what allows the filters and weights in all the layers, from the very first simple edge detector to the final classifier, to be learned simultaneously, just to minimize the overall error on the final digit classification.
That's the incredible power of it. The system learns the most effective low-level features for the specific task it's being trained on, because the learning signal comes all the way back from the final outcome, not from some intermediate hand-designed feature target.
How did they train it specifically?
They used a variant of stochastic gradient descent, stochastic diagonal Levenberg-Marquardt, mentioned in the appendices. It's basically SGD, but with a clever way to estimate individual learning rates for each parameter based on second derivative information, which helps speed up convergence, especially with shared weights.
And the results.
They showed really impressive results for the time, achieving error rates below 1% on the standard MS digit recognition benchmark implied by the dataset size, which was state-of-the-art. The training test error curves they show demonstrate stable convergence after about a dozen passes through the training data.
The paper also makes a point of comparing Linux 5's performance pretty extensively to other methods available back then.
Yeah, that comparison, I think it's section 3 and figure 9, was crucial to really demonstrate the breakthrough. Simple methods like linear classifiers or nearest neighbor methods operating on raw pixels had significantly higher error rates, 8%, 12% error. They just struggled too much with the variability of handwriting.
Okay. What about standard neural nets?
Standard fully connected neural networks, even with one or two hidden layers, performed better, maybe getting down to around 3–5% error, depending on the size. This showed the power of learned features over fixed ones. But they still had error rates several times higher than the Linnet 5.
Why the big difference?
They would likely need far, far more parameters and data to potentially match Linnet 5's performance, partly because they lacked those crucial built-in invariances, the translation invariance from shared weights, the distortion robustness from subsampling that the CNN architecture provided naturally.
So the CNN architecture itself wasn't just a minor tweak. It represented a really qualitative leap for this type of image recognition task.
Absolutely. And they showed the evolution methods like Linnet 1 and Linnet 4, which were earlier and smaller CNNs they had developed, already showed the promise of the architecture even with relatively few parameters. Linnet 5 really pushed the performance further.
They also mentioned boosting.
Right. They even showed that combining multiple Linnet 4 networks using boosting techniques, training them sequentially to focus on errors made by previous networks, could achieve even lower error rates, down to 0.7%. This demonstrated that ensemble methods could push the limits of what even a single powerful model like a CNN could achieve.
Beyond just the accuracy numbers, they also looked at efficiency, right? Like computational costs and memory requirements.
Yes, absolutely. And this was key for practical deployment, especially for things like the check reading system they discuss later. Neural networks, and especially CNNs with their parameter sharing and regular repeating structure, were significantly more computationally efficient during recognition. Fewer multiply-accumulate operations than memory-based methods like k-nearest neighbor or tangent distance, which needed to compare the input against huge databases of examples.
And memory.
CNNs were also much, much more memory efficient. They stored far fewer parameters than the template data needed by those other methods. This made them highly suitable for implementation in specialized hardware, like custom chips, which was a big focus for deploying these systems in the real world, aiming for speeds of thousands of characters per second.
So CNNs really offered this potent combination: state-of-the-art accuracy achieved through learned invariant features, and the computational and memory efficiency needed for practical applications.
That's pretty much the story for recognizing isolated characters.
Hmm.
But, as we discussed right at the beginning, the real challenge is integrating this recognition capability into a complete document analysis system.
Right. Which brings us to the next big innovation discussed in the paper: making those multi-module systems trainable end-to-end using graph transformer networks, or GTNs.
This is where the paper really generalizes the whole concept of gradient-based learning beyond just a single network. The problem with traditional systems, as we said, was that discrete handoff between modules. A segmenter would make a hard final decision about where the characters were, pass that decision on, and any error made there was irreversible and completely invisible to the next module's training process.
So the recognizer never learned to cope with the segmenter's mistakes.
Exactly. GTNs offer a way to build systems where information flows between modules in a way that preserves ambiguity, it doesn't force early decisions, and crucially allows gradients to pass all the way through the entire system.
So the state information flowing between these modules isn't just a final decision or a fixed size vector anymore. What is it?
No. In GTNs, the state information is often represented by graphs, specifically directed as cyclic graphs, with numerical data attached to their arcs.
Graphs. Why graphs?
Think about document analysis. The output of a potential segmenter isn't just, here's the character. It's more like, here are all the possible places a character could be, maybe with scores or penalties associated with each possibility.
Yeah.
The output of a character recognizer running on one of those potential segments isn't just, it's an A. It could be an A with this score, or maybe an O with this other score, etc.
And a graph is a natural way to represent all those branching possibilities and ambiguities.
Exactly. Each path through the graph can represent a different overall hypothesis about the input. For example, a different sequence of characters that could form a word, arising from different segmentation choices and different character recognition outputs along the way. The numerical data on the arcs, scores, penalties, probabilities, whatever, quantify the likelihood or cost of that particular part of the hypothesis.
That seems really powerful for handling sequences or uncertainty.
It is. This representation is particularly handy when you need to incorporate sequential or structural constraints, like using a dictionary of valid words in handwriting recognition. The graph can represent all interpretations consistent with the dictionary.
And graph transformer networks are systems where the modules actually take these graphs as input and output modified graphs.
Yes. A GTN is essentially a network composed of graph transformer GT modules. A GT takes one or more graphs as input and transforms them into a new graph as output.
Can you give an example?
Sure. You might have a segmentation transformer that takes an image, represented as a trivial graph, and outputs a graph representing possible character segments. Then a recognition transformer might take that segmentation graph and, by running a recognizer, like a CNN, on the image patch associated with each segment arc, transform it into an interpretation graph, where arcs represent character possibilities with associated scores.
Okay, modules manipulating graphs. And the magic is that you can actually backpropagate gradients through these graph transformers, even though they're manipulating these structures that seem to represent discrete choices, like which path to take.
This is a really key insight of the paper. While the graph structure itself, the connections, might seem discrete, the functions that compute the numerical data, like scores or penalties, on the arcs of the output graph, based on the data from the input graph, and the module's own internal parameters, can often be designed to be continuous and differentiable, or at least differentiable almost everywhere.
Ah, so the numbers change smoothly.
Exactly. So when a gradient signal arrives at a GT from the subsequent module, telling it how changes in its output affect the final loss, the GT can use backpropagation rules to compute how to adjust its own internal parameters and how to pass gradients back to the numerical data on the arcs of its input graph.
Wow.
It's a powerful generalization of the backpropagation idea to systems where the state isn't just a fixed size vector, but a flexible graph structure representing alternatives and ambiguities.
Okay, let's try to make this more concrete with the example they discuss quite a bit. Handling segmentation ambiguity when recognizing a string of characters, like a word on a check or in handwriting.
Yeah, this is a perfect illustration of the problem and the GTN solution. Trying to perfectly cut a word image into individual characters before recognizing them is notoriously difficult and error-prone, especially with handwriting where characters touch, overlap, or are written cursively.
And getting training data with perfect cuts is hard too, right?
Exactly. Hand labeling training data for segmentation is incredibly tedious and often inconsistent. Different people might segment the same word differently.
So the GTN approach cleverly avoids needing to make that hard segmentation decision up front.
Yes. They use a technique sometimes called hypothesis-oriented segmentation or over-segmentation. Instead of trying to find the one correct way to cut the word, the system finds many plausible places to cut, based on simple image features like minima in projection profiles or gaps between contours.
So it makes more cuts than necessary.
Right. It generates an over-complete set of potential cut points, hoping that the correct cuts are included somewhere within that set. These possibilities are then represented in a segmentation graph. In this graph, the nodes might represent the potential cut locations, and the arcs represent the image patches between pairs of cuts. These are the candidate character segments.
Okay, so you have a graph where each path represents one way to group those candidate segments. Then a recognizer looks at each candidate segment image.
Precisely. A recognition transformer module takes this segmentation graph. For every arc, candidate segment, in the graph, it applies a character recognizer, like Linet 5. It then replaces that single segment arc with multiple new arcs in a new graph, often called the interpretation graph.
Multiple arcs.
Yeah, typically one new arc for each possible character class.
Yeah.
Example, A through Z, 0 through 9, maybe a garbage class. Each of these new arcs carries the score or penalty obtained from running the recognizer on that segment's image patch for that specific character class. It might also include a penalty associated with the segment itself.
So paths through this new interpretation graph represent all the different ways you could interpret the original word image as a sequence of recognized characters, combining different segmentation possibilities and different character choices for each segment.
Exactly that. It's a rich representation of all plausible interpretations.
And then a final step is needed to actually pick the best interpretation out of all those possibilities.
Yes. Typically, they use another GT module, a Viterbi transformer. This module implements the Viterbi algorithm, which efficiently finds the single path through the interpretation graph that has the lowest cumulative penalty, or highest score. This lowest penalty path represents the system's best guess for the transcription of the original word image.
Okay, that makes sense. Now, the really big challenge is training this whole pipeline, the part that proposes cuts, the way scores are combined to minimize the error on the final word transcription without needing explicit labels for the intermediate steps like this was the correct cut, or this segment was actually an A.
This is where the global training criteria for GPNs, discussed in Section 6, become absolutely essential. They explored several different gradient-based methods.
What was the simplest one?
A relatively simple approach, which they call Viterbi training, aims to minimize the penalty of the single best path in the interpretation graph that corresponds to the correct label sequence for the word.
How does backpropagation work through Viterbi?
It's possible because the Viterbi algorithm is essentially based on minimum and addition operations. And they showed earlier how gradients can propagate through a mine operation. The gradient essentially flows back only along the path that was selected as the minimum. So you can backpropagate the error signal from the penalty of the best correct path back through the Viterbi module and then into the recognizer and potentially even the segmenter parameters.
But you mentioned potential problems with that.
Yeah, the issue is that this method only focuses on pushing down the penalty of the correct answer. It doesn't actively do anything about incorrect answers that might also have low penalties. It doesn't explicitly try to create a separation or margin between the correct interpretation and plausible incorrect ones. It could potentially lead to a situation where the penalties for incorrect classes just don't get pushed high enough.
Right. You want the right answer to be low penalty, but also the wrong answers to be high penalty.
Exactly. So they introduced discriminative Viterbi training. This approach aims to minimize the difference between the penalty of the best correct path and the penalty of the overall best path, which could be correct or incorrect.
So it explicitly pits the best good answer against the overall best answer.
Precisely. It tries to ensure that the penalty of the best correct path is lower than the penalty of any other path, including the best incorrect one. This directly tries to build separating surfaces in the parameter space. The backpropagation is interesting here. Gradients flowing back from the best overall path side are effectively negated, pushing up the penalties on the best incorrect path, while gradients from the best correct path side push down the penalties on that path.
That sounds much better for classification tasks.
It generally is. However, it still has a slight limitation. The gradient becomes zero as soon as the best correct path happens to have a slightly lower penalty than the best incorrect path. It doesn't inherently encourage a large margin of separation. You ideally want the correct answer to be significantly better, more confident than the best incorrect one.
Okay, so how do they address that?
This led them to explore criteria based on the forward algorithm, which might be familiar to people who know hidden Markov models, HMMs.
Right. The forward algorithm in HMMs calculates the total probability of observing a sequence, summing over all possible hidden state paths.
Exactly. Here, they adapt that idea to work with penalties instead of probabilities. Instead of just finding the single best path, like Viterbi, the forward algorithm computes a value, let's call it the forward penalty, that effectively sums up, in a log domain sense, the penalties or evidence from all paths corresponding to a given interpretation. A lower forward penalty indicates stronger cumulative evidence for that interpretation, considering contributions from potentially many plausible paths, not just the single best one.
It's like a softer version of Viterbi.
You could think of it that way. It considers the whole distribution of path penalties.
And their preferred training method, the one used in the applications, was often discriminative forward training. How does that work?
This minimizes the difference between the forward penalty computed over only the paths corresponding to the correct interpretation. Let's call this the constrained forward penalty. And the forward penalty computed over all paths in the entire interpretation graph, the free forward penalty.
Okay, why is this generally considered better than discriminative Viterbi?
Because the forward calculation considers all paths, not just the single best one. When you backpropagate the gradient from this difference, it tends to nudge the parameters to push up the penalties of all the paths that are contributing significantly to the incorrect side of the calculation, not just the single best incorrect path found by Viterbi. This encourages a more robust margin between the correct interpretation and all plausible incorrect interpretations. It leads to better discrimination and often better rejection performance.
And a key remark they make throughout this section is that the penalties being manipulated in this GTN framework don't necessarily need to have a strict probabilistic interpretation like summing to 1.
Yes, this is a very important practical and theoretical point. They're not necessarily trying to build a perfect generative probabilistic model of the data like an HMM might. They're building a system that discriminates between the correct output class and all other classes. Trying to enforce strict probabilistic constraints, like normalization, during gradient-based training can be computationally complex and sometimes counterproductive.
So they focus directly on the decision boundary.
Exactly. By focusing directly on minimizing a discriminative loss function, one that compares the score of the correct answer to the scores of incorrect answers, they bypass these difficulties and directly train the system to make the right classification decision at the end of the pipeline. They argue, referencing Vapnik's work, that for classification tasks, trying to estimate the full input data distribution, genetic modeling, when all you need is the decision boundary, discriminative modeling, can be theoretically suboptimal. You solve the problem you need to solve.
Okay, so GTNs provide the flexible graph-based structure, and discriminative forward training provides a powerful objective function to train that structure end-to-end, focusing directly on the final task performance.
That's the essence of it. It's really about applying the core principles of gradient-based learning and backpropagation to the much broader problem of composing and optimizing multiple complex processing steps represented as graph transformations.
Now, while this hypothesis-oriented segmentation combined with GTNs offers a clever way to handle segmentation ambiguity by exploring multiple possibilities, it still relies on some, heuristic image processing module to find those initial candidate cuts in the first place. Was there an alternative approach presented that avoided even this initial explicit segmentation step?
Yes, absolutely. That's where space displacement neural networks, or SDNNs, come into the picture. Section 7. It's a conceptually simpler yet very powerful approach that's particularly well suited to leveraging the inherent properties of CNNs.
Okay, what's the core idea of an SDNN?
The basic idea, instead of trying to find specific cut points to segment characters first, you just take a trained convolutional network, essentially a character spotter recognizer, and you replicate it, sliding it across the entire input field like an image of a word or a line of text.
So, like scanning the image with a recognition window, and at each position, the window outputs scores telling you what character it thinks is centered there.
Precisely. But the key is that doing this repetitive scanning with a convolutional neural network is highly efficient. Because of the shared weights in the convolutional layers and the local connectivity, replicating a CNN across an image field doesn't require recomputing everything from scratch at each location. It's computationally equivalent to just having a larger CNN with expanded feature maps in the later layers. The computations for the overlapping receptive field areas are effectively shared.
Right. The convolution operation itself handles the scanning efficiently. And because CNNs are inherently robust to small shifts and distortions.
Exactly. That's the beauty of it. The SDNN approach leverages the CNN's built-in robustness. The network can detect a character reasonably well, even if it's slightly off-center or distorted within the scanning window's receptive field.
Does this help with touching characters?
Crucially, yes. They showed that this approach could implicitly learn to handle tricky situations like touching or even overlapping characters. It could even learn to correctly associate disconnected ink components that visually form a single character, like the parts of an eye or fragments of a broken character. The network learns to interpret the complex visual patterns arising from these challenging segmentation situations without needing an explicit segmentation algorithm trying to draw boundary lines between characters first.
So it sort of addresses the feature binding problem, figuring out which visual features belong together as one object just through the learned representations within the CNN itself.
In a sense, yes, it learns to map the complex local visual evidence directly to character classifications at different positions.
So the output of this SDNN scanning process would be what, a sequence or grid of data?
Yes, the output is typically a sequence of vectors, if scanning along a line of text, or potentially a 2D map, if scanning a 2D image for objects. Each vector or map location contains scores or penalties indicating the likelihood of each character class being present at that specific location or centered in that receptive field.
And this output might be noisy. Multiple hits for one character, maybe some false positives where there's no character.
Absolutely. The raw SDNN output often produces multiple detections for a single character as the window slides over it, and might also generate spurious detections in blank spaces or noisy areas. So this noisy output stream needs interpretation.
And how is that interpretation done? Back to GTNs.
Yes. Typically, a graph transformer network is used to extract the best actual label sequence from this noisy SDNN output. The SDNN output sequence is first converted into a linear graph, sometimes called the SDNN output graph or recognition graph. In this graph, nodes might represent locations along the scan, and the arcs leaving a node represent the different candidate character classes detected at that location, weighted by their scores or penalties from the SDNN.
Okay, so a graph of local character hypotheses. How do you get the best overall word?
You then usually use another GTN component, often involving composition with linguistic constraints. For example, you might have a grammar transducer, like a finite state transducer, FST, representing a dictionary or a statistical language model. A GT module then performs composition, using the generalized transduction mechanism we discussed, between the SDNN's output graph and this grammar graph.
What does that achieve?
The resulting interpretation graph contains only paths that represent valid interpretations,
Yeah.
for example, actual words from the dictionary, that are compatible with the sequence of character hypotheses generated by the SDNN. The penalties on the paths reflect both the SDNN's recognition scores and potentially language model scores. Finally, Viterbi search, or maybe beam search, a pruned version, for efficiency, is used on this interpretation graph to find the single best path, which corresponds to the final recognized word sequence.
And crucially, this whole SDNN plus GTN interpretation pipeline can be trained globally end to end.
Absolutely. That's the key advantage. You train the entire system, the weights of the CNN being replicated inside the SDNN, and the parameters of the GTN modules that interpret its output all together using a global loss function like discriminative forward training, based only on the final whole word or string labels. You don't need to provide labels for individual characters or specify segmentations during training. The system learns to handle the segmentation ambiguity implicitly as part of optimizing the overall recognition task.
That sounds incredibly powerful, letting the system figure out the segmentation implicitly, and they showed that SDNNs weren't just for characters either.
That's right. They point out the same principle applies more generally to object detection in images. A CNN can be trained to distinguish a specific object class, like faces or cars or maybe address blocks on mail pieces from the background. Replicating this trained CNN as a 2D SDNN over a larger image allows the system to efficiently spot instances of that object.
How do they handle different object sizes?
Often by processing the image at multiple resolutions or scales, running the SDNN on each scaled version. And again, the ability to potentially train this object spotting system globally, perhaps using image-level labels indicating only the presence and approximate location of objects, could avoid the need for meticulously drawing bounding boxes around every single training example.
This whole concept of training a spotter, like the SDNN, and an interpreter, the GTN, together, end to end, feels like a really major theme for tackling tasks where segmentation or exact localization is inherently difficult or ambiguous.
It is. It's a recurring theme in their work in philosophy. Avoid explicit, potentially brittle, intermediate decision steps whenever possible. Instead, try to learn the entire mapping from the raw input data all the way to the final desired output using the power of gradient-based optimization.
The paper also takes some time to place GTNs within a broader context, particularly linking them to weighted finite state transducers, or WFSTs.
Right. WSSTs were already becoming, and are now very widely used, in fields like speech recognition and natural language processing. They provide a powerful mathematical formalism for representing things like pronunciation models, dictionaries, grammars, and even acoustic models as graphs with weighted transitions. WFSTs allow for elegant algorithms for operations like composition, combining models, shortest path search like Viterbi decoding, and determining equivalence.
So how do GTNs relate?
GTNs can be seen as a generalization and, perhaps more importantly, an operationalization of the WFST framework specifically for the purpose of gradient-based learning. While traditional WFST work often focused heavily on the algebraic properties and efficient search algorithms, the GTN framework provides a systematic methodology for actually training these graph manipulating systems, especially complex cascades of them, end-to-end using gradients derived from an overall task loss.
And they introduced this concept of generalized transduction to handle situations where the data flowing through the system, the information on the graph arcs, wasn't just simple discrete symbols or scalar weights, but potentially richer continuous data like feature vectors or even image patches.
Exactly. Standard WFST composition operations are typically defined for arcs labeled with discrete input-output symbols and weights from a semaring, like probabilities or log probabilities. Their generalized transduction concept extends this idea to allow the composition of graphs where the arcs carry more complex numerical information.
How does that work?
It involves defining a composition transformer object that specifies the rules for combining arcs from the input graphs. It needs two key methods, essentially. A check function that determines if two arcs, one from each input graph, are compatible and should potentially combine to create arcs in the output graph. This establishes the structural connections.
Okay. And if they are compatible,
Then an fprop, forward propagation function is called. This function computes the data, example, feature vectors, penalties, for the newly created arcs in the output graph as a differentiable function of the data on the original input arcs and any internal parameters of the composition module.
Differentiable is the key word again.
Absolutely. Because for backpropagation, there needs to be a corresponding BPOP method that can compute the gradients of the overall loss passed back from the output graph with respect to the input arc data and the module's parameters. This requires that the fprop computation be differentiable.
So it allows gradient flow through the graph composition.
Precisely. It lets you seamlessly integrate, for instance, a graph representing linguistic constraints, like a dictionary, which might have discrete symbols and simple penalties, with a recognition graph coming from a neural network, which might have arcs carrying complex feature vectors or continuous course penalties, into a single end-to-end trainable system. Standard WFST transduction is just a special case of this.
So even these complex structural operations involving matching paths in different graphs are formulated in a way that's compatible with the flow of gradient information for learning.
That's the underlying principle they established. While the graph structures themselves might represent discrete choices or sequences, the numerical values that determine which paths are preferred and contribute to the final loss, the values that are being learned via the parameters, are treated differentiably, allowing the entire system to adapt.
Okay, we've covered a lot of the core technical ideas. Gradient-based learning, CNNs, GTNs, discriminative training, SDNNs, generalized transduction. Let's look at how they actually applied this entire framework to solve real-world problems, proving its effectiveness in practice. They detailed applications in online handwriting recognition and a check reading system.
Yeah, these applications are really the combination of the paper, demonstrating how the theoretical framework translates directly into practical, high-performing solutions for genuinely hard problems. Online handwriting recognition, where you capture the pen's trajectory over time using a stylus on a tablet.
Right, not just a static image.
Exactly. It's challenging because of the huge variations in writing style. Print, cursive, mixed, the ambiguity of characters written in isolation, and the critical need for word-level context to figure out what was written. It looks like E, it looks like V, etc.
So how did their system tackle this using the GTN approach?
Their system followed the GTN pattern quite closely. It typically had modules to pre-process the raw pen trajectory data, maybe normalizing it, extracting features like position, velocity, curvature. Then they might use a replicated CNN, essentially an SDNN adapted for these sequential online features, which acted as a character spotter scanning along the trajectory path.
Okay, so the SDNN outputs character hypotheses at different points in time or space along the stroke.
Right. The output of the SDNN would be represented as a graph, maybe a linear graph where nodes correspond to points in time, and arcs represent the character hypotheses with scores from the CNN at those points. This recognition graph was then fed into a GTN interpreter.
What did the interpreter do?
It would incorporate more detailed character models, perhaps HMM-like structures represented as GTs, as shown in Figure 27, and crucially, compose the output with a dictionary or a statistical language model graph. This composition restricts the possible interpretations to valid words or likely sequences. Finally, a beam search transformer, which is essentially a pruned Viterbi search GT, would find the best scoring interpretation paths through that final composed graph.
And the key again is that the whole thing from the SDNN processing the trajectory to the language model interpretation was trained globally.
Yes, absolutely.
Yeah.
Using the discriminative forward criterion trained at the word level. This meant they didn't need to manually label individual characters or specific segment boundaries within a word for training. The system learned end-to-end to map the raw pen trajectory of a complete word directly to the correct word transcription.
Did global training help?
Significantly, they showed experimental results, like in Figure 32, where this global training approach provided substantial improvements in recognition accuracy compared to training the modules individually, especially when a dictionary was used to constrain the outputs. It confirmed the benefits of end-to-end learning that had also been seen in speech recognition.
Okay, now the check reading system. That sounds like a truly industrial-scale challenge with serious economic implications.
It absolutely was. Automating check processing, particularly reading the handwritten or machine-printed amount, was a major goal for banks. But it requires extremely high accuracy and, just as importantly, a very reliable way to reject checks the system isn't confident about, sending those difficult cases for human review. Getting the rejection right is critical.
So they built a full GTN-based system for reading the check amount.
Yes. Figure 33 shows the architecture. It's a cascade of graph transformer modules.
Can you walk us through that pipeline?
Sure. It starts with the image of the entire check, represented as a single arc in a graph. The first module is a field location transformer. This uses more classical image analysis techniques combined with trainable components to identify candidate regions on the check where the legal amount, the written out amount, or the courtesy amount, the numerical amount, might be located. Its output is a field graph where arcs represent these candidate amount zones, carrying the image patch for that zone, and, importantly, a differentiable penalty based on features indicating the confidence that this is the correct field.
So even the field location confidence is part of the trainable system.
Yes, its parameters could be adjusted during global training. Next, a segmentation transformer examines the image patches within the located field zones. It uses heuristics, maybe based on connected components or techniques like hit and deflect they mentioned for separating touching characters, to find candidate cut points. It outputs a segmentation graph, where paths represent different ways of grouping segments, and arcs carry the segment images and potentially another differentiable penalty related to the segmentation quality.
Making the segmentation step itself trainable based on downstream recognition seems like a huge advantage over fixed segmenters.
It's a massive deal. It means the system can learn to adjust its segmentation strategy, maybe be more aggressive or less aggressive with cuts based on what ultimately worked best for getting the final amount recognized correctly. Then comes the recognition transformer.
Running Linnet 5.
Exactly. It runs their pre-trained Linnet 5 CNN on each candidate segment image coming from the segmentation graph. This transforms the segmentation graph into a recognition graph, essentially a weighted trellis. Each segment arc gets replaced by maybe 96 arcs, one for each character class they recognized, digits, letters for amounts, symbols, plus a rubbish or reject class. Each arc carries a penalty combining the original segment penalty and the penalty or negative log likelihood from the Linnet 5 recognizer.
So now we have a graph of scored character possibilities based on the segmentation hypotheses. What's next?
Next is integrating grammar. A composition transformer takes this recognition graph and composes it with a grammar graph. This grammar graph encodes the rules for valid check amounts, for example, sequences like $150. This composition uses their generalized transduction mechanism. The check function ensures character compatibility, and the fprop function sums the penalties along valid paths. The output is the final interpretation graph.
Containing only grammatically valid interpretations of the amount field.
Correct. And finally, a Viterbi transformer runs on this interpretation graph to select the single path with the lowest overall cumulative penalty. That path represents the system's final interpretation of the check amount.
And this entire complex pipeline, from finding the field to segmenting, recognizing, and applying grammar, was trained end to end.
Yes. While individual components, like the Linnet 5 recognizer, would certainly be pre-trained on large data sets of isolated characters first, the crucial step was that the entire system, including the parameters influencing the field location penalties and the segmentation penalties, was then fine-tuned globally using the discriminative forward criterion. The loss was calculated based on the correctness of the final check amount interpretation for a whole check image. No need for manual segmentation labels on the checks used for this global fine-tuning. The gradients flowed all the way back.
That's really impressive. How did they handle the absolutely crucial aspect of rejecting low-confidence checks? You can't afford many errors in banking.
Right. They needed a reliable confidence score. They came up with a very elegant solution that cleverly leveraged the architecture they already had for discriminative forward training.
How did that work?
Remember, the discriminative forward loss compares the forward penalty of the correct answer's paths to the forward penalty of all paths. They realized they could reuse this exact computation, but instead of feeding in the true correct label, they feed in the system's own best guess, the answer produced by the Viterbi step as the target sequence.
Okay. What does that give you?
The resulting loss value calculated this way serves as an excellent confidence score. It's related to the negative log probability of the system's own chosen answer, considering all the evidence supporting it versus all the evidence supporting alternatives. A low loss value here means the system found a highly plausible, low penalty set of paths corresponding to its chosen answer, indicating high confidence. If this loss value was above a certain threshold, the check was rejected as low confidence.
That's really neat, using the same training framework machinery to derive a confidence measure needed for practical deployment. It shows the coherence of the whole approach.
It does. And this check reading system, based on these GTN principles and global training, was genuinely groundbreaking. It was one of the first systems to achieve the kind of accuracy and rejection performance thresholds required for commercial deployment in the banking industry, really validating the power of the GTN framework and the global gradient-based training philosophy on a major real-world industrial problem.
Okay, so looking back at the whole paper, it really brings together several incredibly powerful and groundbreaking ideas.
It absolutely does. It powerfully solidifies the argument that gradient-based learning isn't just for training simple networks. It's a powerful, general organizing principle that can be applied to learning in large, complex, multi-stage systems.
CNNs provided the core muscle for the image understanding components.
Right, by providing an architecture with built-in translation invariance and distortion robustness, learned features, and parameter sharing for efficiency, all trainable end-to-end.
And graph transformer networks provided the essential framework to actually build and train those complex multi-module systems.
Exactly. By allowing ambiguous state information to be represented flexibly as graphs, handling sequential structure naturally, and enabling backpropagation to flow through multiple, potentially dynamically constructed modules, integrating things like segmentation, recognition, and grammar.
And the discriminative training criteria, especially discriminative forward training, were key to optimizing the system directly for the final classification decision and for robust rejection.
Yes, providing effective training objectives that focus on separating correct from incorrect answers, often proving more practical and effective for classification and rejection than trying to enforce strict probabilistic modeling throughout the pipeline.
And let's not forget SDNNs, offering that powerful alternative to explicit segmentation by learning to spot objects and characters implicitly within the network.
Right, integrating spotting, segmentation, and recognition through the power of learned representations in replicated CNNs trained with end-to-end gradients.
And the paper didn't just present these ideas in theory, it crucially demonstrated them working successfully on really challenging commercially relevant applications like reading checks and online handwriting.
It was a powerful proof of concept. It showed the potential of this integrated gradient-based approach to replace brittle, hand-engineered systems, where modules were optimized in isolation, with flexible, globally trainable systems that learned how to perform complex tasks much more effectively.
So what does this all mean for you, our listener, today?
Well, I think this paper makes a really strong case, as they state in the conclusion, that gradient-based learning is a general organizing principle for learning in large systems. And they suggest it can be applied whenever the task involves processing information through stages, and where domain knowledge or the state information can be represented by graphs.
So think about the complex systems you interact with, or maybe the challenging data analysis problems in your own field or research. How many of them involve a sequence of steps where decisions are made, information is transformed, and where ambiguity or uncertainty exists at intermediate stages?
Yeah, think about natural language understanding, translating sentences, analyzing complex sensor data streams, certain types of medical image analysis or diagnostic processes, even interpreting scientific data, often involves processing ambiguous inputs through multiple stages of analysis to arrive at a final conclusion or interpretation.
Could these principles representing intermediate steps as graphs to maintain ambiguity, designing modules whose computations are differentiable, and training the entire pipeline end-to-end using a global discriminative objective function offer new ways to build more robust, more accurate, and more automated systems in those domains?
What previously intractable problems, maybe problems that relied heavily on hand-tuned heuristics and fragile interfaces between modules, could potentially be solved more effectively by replacing those discrete steps with a globally optimized differentiable flow of information, learning directly from the input data to the final desired output.
That's a really powerful question to sit with. The ideas laid out in this paper nearly 3 decades ago are undeniably foundational to so much of the incredible progress we've seen in machine learning and artificial intelligence since its publication.
They certainly are. That's a landmark work.
Thank you for joining us for this deep dive into a truly influential piece of research. We hope you gained some valuable insights into how these complex end-to-end learning systems were first conceptualized and successfully built.
Thank you. It was great discussing it.
We'll see you next time on The Deep Dive.